This original Xbox is the first in the world to ever have as much as 256 megabytes of memory. I've been working on this project for 2 years, and this video will show you my journey from a very technical point of view. You will see reverse engineering, hardware development, software hacking, and hopefully experience some of the roller coaster that I've been on. Now, imagine this. I've just finished my 128 megabyte upgrade of the Xbox 1.6, and I'm thinking, what's next? Maybe even more RAM? Is this even possible? To find out, I need to make a proof of concept. Now, a lot of people had the same reaction when watching the original video, which is that if you can use this method to double the memory on the 1.6, why can't you use it to double the memory on the rest of the versions as well? The problem with that is that the signals that we're tapping into here on the underside of the board, see my previous video if that doesn't make any sense, these are the same signals that are seen on the other revisions, meaning there's no new signals here. This is just hooking up the same chips in exactly the same way on the 1.6 as the other versions. So this is not some kind of magic bullet. What we need is something novel. So my first thought here was I need to understand how this addressing works. So what I did was I found the datasheet of that chip that the Xbox uses, and here's a list of the pins. So of interest are the address pins here, A0 to A11. If you just look at that without thinking about how the addressing works, then that is not enough bits. Right? If you have 8 chips and you have 12 bits, then this is nowhere near enough memory. But the trick is that there are rows and columns. So a word of data is addressed by a column address plus a row address. So effectively you get 12 bits in the row address and an extra 8 bits in the column. And that was the first clue that I got. So why is the column address limited to only these bits? We have more bits, so can we just add another bit and then get double the memory? So I started looking into how the Xbox registers are working here. I knew there were a couple of addresses that provided some configuration of the memory. So I started looking at open source NVIDIA drivers to see if they have any clues. What I found is this from NVTools for the NV10 architecture. Now the Xbox is NV2A, which is pretty close to NV10. So I thought this was a reasonable place to start. So we got this register CFG1, and a value is extracted from this called colbits. That stands for column bits, so how many bits are addressing columns. And what they do is they shift the register by 12, and then they mask off 4 bits with this mask 0xF. So this register also exists on the Xbox, and when you check out this operation, then it gives you the value of 8, which is exactly the number of column bits as the real hardware is using. So that's a really good sign. So what I'm thinking is we just bump that to 9 and see what happens. But how are we going to know if bumping up to 9 even does anything? How do we know it has the intended effect? So I build this setup. What I'm doing is breaking out select pins of that RAM address bus and control bus and routing them to a logic analyzer. This lets me observe how the Xbox is trying to address the memory. Then I can have a modified BIOS. I used a BIOS in this case just because it's very low level. I'm needing a low level access here. And I used the open source XBlast, my go-to tool from my previous project where I also had to modify XBlast. So I used XBlast. Now for my logic analyzer, I have set up the Xbox to switch to 9 column bits and then run through the address space. Just doing a simple read or write, just again access that I can see on the logic analyzer. So that's what's going on here. We're seeing an increase in the address bus value as I'm going through memory. So we quickly see it ramp up from A2 to A3, all the way up to A7. So A7 goes high for a while, then that overflows. It doesn't overflow to A8, it overflows to another address bit. But yeah, the critical thing here is that A8 is not being used for addressing. This means there are 8 column bits, because it's A0 to A7. Then I switch to 9 column bits, and this is amazing. We can see that now A8 is used at that rollover point, where previously the value just went back to 0. Now we roll over to A8. A8 becomes active. We have 9 column bits. So this looks really good. Also, this took a long time to develop such a clear view as this. The Xbox uses DRAM, which implements refreshing. It has to refresh to keep its value because it's an array of capacitors. Those capacitors discharge by leakage, so refreshing is constantly ongoing, and this is what it looks like when you have refreshing enabled. It's preserving the value of that memory, but then it's really obscuring my view of what's going on. In particular, this A8 bit is obscured. This is unusable to me. I can't even tell if it's using that bit. Then another thing, so there is this special pin, the AP pin. Here it says column address CA8 is used for auto precharge, the AP pin. This AP pin is necessary for this refreshing operation. What I found is that when I set the column bits to 9, then this activity on A8 stopped. It was no longer being used as an AP pin. To me, this seems like a bug in the Xbox hardware, and this meant that I really could not use the system in this configuration because, yeah, without auto precharge, you don't get refreshing, which means you get RAM corruption very rapidly. I also found datasheets from various memory modules that have 9 address bits, and they kept the address bit on A8. Despite that being part of the column address, that's not a limitation. They kept on using A8 as the auto precharge pin. So now I needed to work around this issue. And it is very fortunate that at this point I stumbled across the Xbox source code leak. So there's this repository, Xbox leak May 2020 on GitHub. You can find it very easily. And it contained a very interesting file called nvref2a.h. This is basically a register listing of all the registers on the GPU. The GPU contains the RAM controller, so that's why it's relevant here. And now I no longer have to use that open source code. I can use the actual code that NVIDIA provided to Microsoft. So now we're looking again at this CFG1 register. We can see that column bit count register that we're looking at, the value for 8, it's 8, and 9 is also listed. Interestingly, we've got 7 as well as 10. I came across 2 interesting fields. So there's APA and APB. And AP here stands for the auto precharge. And then it's got these various options. So the default is 0, which is A8. And yeah, this is telling me that it's using A8 as the auto precharge pin. And what's nice is I can change that. I do have some choice to change that auto precharge pin. You might think that this is not very useful because we want it on A8. If I switch it to A9, then it is on the wrong pin. This is not useful. However, because of the nature of addressing, we are basically free to change pins. If I switch A10 and A11 in the hardware, then this is no problem at all. Actually, I posted about this on the forum as a bit of a teaser. Here I connected 2 wires to switch the A8 and A9 pins. And I repeated it on every chip. And after a BIOS mod to set this register, it worked perfectly. And this was the critical part of the proof of concept that I needed, that I can switch those pins. I can use the column bits set to 9. And then with the right chip, it should work. I also experimented with values such as this, increasing the column bits to 10, 11, 12, and so on. I found that while the GPU thought that it had more memory, it was not using additional column bits. there is most likely a strict hardware limitation that you just cannot go above 9 column bits. Which is interesting because if you check the microarchitecture of that GPU on Wikipedia, someone has added a note that says the max VRAM size is 128 megabytes, which may be true for the desktop versions, but as we'll see for the Xbox, that is not the case. Let's take a look at what chips could possibly support this. So I've put in some filters into DigiKey here, sorting through things such as memory size. For memory size, that is 256 megabits, because the stock memory is 128 megabits, so we want double this. Also important to note is the organization here. So 32 bits, 4 banks, and 1 megawords. So we want a similar organization. We want 2 megawords with 32 bits. So I've plugged that into here, and we get 12 chips. They're all, most of them are obsolete, of course. This is a very old technology. It's only a single DDR DRAM. Now we're up to like DDR5, DDR6, that kind of stuff. So here it's showing 8 meg times 32. That's okay, because that is 4 banks times 2 megawords. Now, worthy of note here is the options for the package. We've got this 90-pin BGA, this 90-pin BGA, and 144-pin BGA. They're all BGAs. Whereas the stock chip is a TQFP. That means it's a thin quad flat pack. And it has leads. Whereas these BGAs do not have leads. BGA is a ball grid array. This is clearly a problem because now we can't just plug it in to the Xbox, replacing one chip for the same chip of the same size. We have a different package, so we need an interposer. An interposer is essentially just an adapter from one footprint to another. In this case, we're adapting from that TQFP, which is on the Xbox motherboard side, to the BGA, which is on the memory side. So what I did was I put together this PCB in KiCad. It looks pretty complicated, but really this is just basically plumbing. I have pairs of pins throughout these 2 chips, and I just need to wire them together. Really quite easy. The hardest thing is just routing. So this one is 4 layers, and you see sometimes there is some contention in those layers. You have to snake some signals in and out. But really it wasn't too challenging. Going to the 3D view, we can start to see what this is going to look like. One thing to work out is how to connect this to the Xbox. So in this case, you can see I've put these very short pads on the bottom side. So this is going to surface mount onto the motherboard. My problem is that's going to be very hard to solder. That's essentially soldering a BGA. So instead, my idea was to sand down these edges so that we expose half the via. And then the via becomes what's known as a castellated edge, where you have metal connections on the edge of the PCB. A lot of PCB vendors will give you the option for castellated edges, but they will not give you the option at this pitch. You see here the minimum size of a castellated hole edge to edge is 0.6 millimeters, which is essentially the whole of our pitch. Edge to edge is only 0.45 millimeters, a lot shorter than the capability. So since they cannot mass produce these castellated holes, I decided to do them manually. Here's a look at the PCB that's been sanded down. The edges I have soldered to. That's why it's silvery rather than coppery. The edges are not particularly solderable. I made a mistake here by allowing the solder mask to go down these vias, whereas I should have excluded that, and then we would have a cleaner edge. But that's okay, it didn't present any problems. Here's a PCB before sanding. So you can see on the edge there are no connections, only on the bottom. If you read online, you'll find that a lot of people are quite afraid of BGA, and I suppose I was too. This is my first time really doing BGA soldering, and I did not have good equipment at all. I used a heat gun. These things are meant for stripping paint off the wall. It's not for doing precise soldering, but I made it work. It was good enough for the time. Though saying that, I had missing connections rather than short circuits, primarily. It went extremely well for the first 4 chips. Here's a look at the X3 BIOS, the config live, showing 128 megabytes, but I only have 4 chips installed in the Xbox. So that was really cool. That was a nice proof of concept. And then I just had to do the remaining 4 chips, which was where it got more difficult. I had multiple faults on those next 4 chips, and I also had quite an issue with clocking. For some reason, adding these extra chips made it so that the timing was now off, and I was getting loads of memory errors. I wasn't able to boot anything. Then I discovered a few settings that fixed that. I still needed to decrease the memory clock, but it was not so significant. So there's a look at the whole proof of concept. I went from really not knowing how DRAM was organized or refreshed or anything like this, to understanding how it's implemented in the Xbox, how to add more memory, understanding what parts are on the market and available, implementing a PCB, and getting it to work. Now that I've made my first prototype and I know that it works, I was thinking I want to start producing these for the community as well. I'm expecting there's going to be some interest. People are not going to want to assemble them themselves, especially with needing BGA soldering. So I was thinking of producing these modules, maybe a small batch production at something like the scale of 100 Xboxes. So that would mean 800 modules. And then sell those so that they're achievable for the home Xbox modder. The problem is the current design with the green PCB is not scalable. The fact that there is a manual process to have to sand down the edges, and I don't have a machine to do that for me, that makes it not scalable. It takes too long, it's error prone, and it doesn't produce a nice result anyway. So what I need is a different design that is easy to install, easy to manufacture, and easy to test. I was searching for inspiration when I came across PCBWay's rigid flex PCBs. And this means the PCB is partially FR4 fiberglass, that is a rigid PCB, standard PCB material, and partially it is flex, so this is usually polyamide based, and it's a high temperature polymer with a copper deposited on it for the traces. This is a pretty nice solution because the flex can stick out of the PCB and it can be very easy to solder. It can be a lot thinner than the rest of the PCB. So then I can treat those pins more like the standard legs of a TQFP package. In the case of PCBWay, I was forced to have a stack up where the 2 inner layers are flexible and the 2 outer layers are rigid. But this is okay because the flex can bend down and still manage to touch the motherboard. I came up with this board design which is very similar to the previous one, only now the pins are exposed and more sticking out to the edge. The 3D view in KiCad doesn't really show this properly, but you get an idea. I ordered these from PCBWay. They were manufactured and delivered in just a couple of weeks, and when I got to testing them, they worked immediately. Then what I started doing was checking that I can manufacture these more rapidly. So this is my kind of setup here. I can solder 2 devices at once. What I did was I upgraded from that heat gun. Now I have a proper hot air station, so I can control the temperature most critically. I use this tacky liquid flux. This sticks to the PCB quite nicely. It doesn't get messy. It actually really contains itself under the BGA, which is really nice. This is only a 2-step process, so first I solder on the BGA, and then secondly I have to add the solder bridges on top of these pads. All in all, it takes about 10 minutes to do 8 parts, so that's for 1 Xbox, and that's a pretty good amount of time. Now for the part that took the longest of all. It is testing. So I don't want to be making an unreliable product, so that means I need to test. I need to make sure that it's not only the BGA that is operational, but also its connection to the interposer and the interposer PCB itself, that are all manufactured properly. I definitely do need to test the BGA because these come from China. I'm sure they're being resold. It's going to be some new old stock or perhaps even recycled devices. So that is the most critical part to test, but also I know my BGA soldering is not always perfect, so that is also very important to check the solder joints. If I only wanted to test the BGA, then there are solutions for this that exist already, called BGA sockets. These, I imagine, would not be too expensive, but it just doesn't provide the level of testing that I need. So what I need is an end-to-end test, a system-level test, where I'm putting the chip in an Xbox, and the Xbox tries to use the memory and tells me if it's working or not. I can create a custom BIOS for the Xbox that will test the device as soon as the Xbox is powered on, and it will tell me on the front panel LED if that chip has passed or not. This allows for the testing to be very rapid. I looked around for some kind of socket or even just a standard connector mount that I could use for these interposers for the test system, but I simply couldn't find anything. So I'm forced to make my own solution, to make my own test jig. My first attempt was this springed pin, kind of a Japanese temple looking thing. I think it's pretty cool, but it didn't work very well. These pins are 0.68 millimeters wide, and the pin pitch here is 0.65 millimeters, so I had to stagger them. If you look closely, they're in 2 rows here. And it took quite a long time to get this assembly properly sized for these pins, because I was using a laser cutter, and the precision required was quite fine. If I spend too much time lasing a hole, then the hole will be too big and the pin won't be precise and it will be wobbling about. If I don't spend enough time, then I simply cannot insert the pin. The idea behind these pins is that they have a spring in them, so any non-linearity in that interposer would be leveled out by the springs. The spring force on each one of these pins was something like 70 grams, but when you have 100 pins, then that adds up to about 7 kilograms of force required to fully depress this. I typically applied about 4 kilograms. Still, this is a lot of force in a small area, and when I'm pressing on the top with my fingers or thumbs, that can be extremely tiring. So actually, I found this setup quite painful to use. My attempted workaround for that was the hammer. I built this out of a microwave oven transformer and just some wood that I had lying around. And the idea is that this transformer, which is something like 4 kilos, would be able to press on that and provide the right amount of force. The trouble with the hammer was that it just wasn't precise enough. I had 2 major problems with this design. The primary issue with this design was alignment, and when I'm applying force through that hammer solution, then I just cannot control the alignment finely enough to have any success in testing chips. So the success rate of this setup, the true positive rate, was something like 20%, or maybe even lower. In an attempt to fix the alignment issue, I made this. Is 3 layers of 1mm acrylic. The idea was that the middle layer can key onto the BGA. You see the square in the center is perfectly the same size as the BGA chip. And then this can provide the alignment that will get the pins aligned on the springed pins of the tester. I think this was a good idea, but it was flawed in 2 ways. Firstly, the alignment of the BGA to the pins on the interposer is not precise. They are on different layers. So the BGA is positioned on the top layer of the PCB, and those pins are on the middle 2 layers. And these can have some mismatch. The second issue is that we don't have any precision on the spring side of this system. Those springs wobble around quite significantly on the top end. This is only a theory because I could not observe those pins while I was pressing down. This is also another issue with this system, is that I cannot observe how those pins are making contact, if they are making contact. At this point, I was really thinking about how do I change this system so that it can work more reliably. And so I realized that there is a kind of redundancy here. The flex part is flexible, and the amount that it's flexible is not so much, just a bit. So I really don't need these pins that have, a displacement of something like 7 millimeters. I don't have anywhere near that much displacement on the flex. So what I actually need is a rigid side on the Xbox, on the tester, and then I need some force from above that will press that flex onto the tester. So this is what I came up with. I got a bunch of thin pins and I soldered them onto the footprint on the Xbox side. The idea is that the interposer can sit on top of those so that the flex is the only thing that is contacting, and then I can apply pressure from above with a part such as this. I have deposited silicone onto this piece of acrylic. The silicone is very flexible so that it can fill all those gaps, apply a nice even pressure to straighten out the flex and to make contact to the tester. Here are some of the supporting parts that I made for this. For example, I need this piece to be the mold for the silicone. I also experimented with not using silicone but using hot glue instead. Hot glue is a lot firmer. It still has some play to it, which is good. The problem with hot glue is that it's really quite sticky, so I couldn't get it out of the form without destroying it. However, this solution was really just as bad as the previous one. Maybe slightly better, but nowhere near what I needed. So what I decided to do is do a little bit of debugging. So I built this PCB that lets me see when there is contact being made. Here I'm just playing around with it, but you can see how difficult it is to get all the LEDs lit at once. I also did some single pin debugging with this solution. Even those 6 points of contact didn't provide an even contact around the whole device. Finally, I realized that this solution with the silicone is not providing a good contact patch. Due to the width of the silicone here, a lot of force is being wasted. I'm applying pressure to the top, but that is not providing pressure to the electrical contacts. So what I really needed was a very thin line, about 1 millimeter thin, to provide force onto the flex and then onto the electrical contact. So that's when I came up with the winning solution. I got this very thick bit of acrylic, relatively thick, I think it's about 4 millimeters, and I found this silicone string on eBay. It's meant for use in jewelry or something like that, arts and crafts, but this see-through silicone was really perfect. It was just springy enough, it deforms very slightly, it is also see-through, that is great. I attached it to the acrylic using super glue, and super glue is also see-through. So together I could see all the way through from the top to the pins that I'm trying to make alignment with. And because I can do that, then that solved my alignment problem. I can just align these visually and I can get it right and I can get it very precise. I essentially gave up on a mechanical alignment solution. I also had a problem on the tester side that those pins that I hacked together, that I just soldered onto the motherboard, were completely misaligned. Some of them were at strange angles, and I think that was never going to work. So I just made a PCB. You can get such great accuracy with the PCB, and I can also have it gold plated for great contact. I really like how this one looked. I had to cut out some parts of the edge of the PCB to fit it flush with the motherboard, so it looks like it has a kind of crazy hairstyle. With this solution, I got about 80% true positive rate, and this is definitely good enough. So that means when I assemble one Xbox worth of chips, maybe I have to retest one chip, and that brought my overall testing time down to about 2 minutes. For context, to test a single chip, the Xbox needs to be powered on for about 10 seconds. And this is the final design I settled on. I think it's quite efficient. It's definitely good enough for the level of production that I'm going for. Due to the concentration of force with the silicone string, I don't even need to apply that pressure onto the top either, so my hands don't get tired. Although I am considering building a piece that goes over the top of the Xbox that I can use leverage to apply more force very easily. This is one of my early ideas that I tried to get through JLC PCB. The idea was that by staggering the castellated holes, then I could be able to satisfy that 0.6 millimeter edge-to-edge castellated hole distance requirement. Unfortunately, on design review, the technician at JLC PCB refused this design. They rightly claimed that these edges would likely snap off, especially in routing the PCB, and I think they had a problem also with the drill size, that they would need to put a very small drill into this cove. Despite that, I still have a soft spot for this design. I think it's pretty cool. In parallel to all of the hardware development, of course I've had to do software development as well. The hardware does not just stand on its own, it needs software support. So to explain how the software is working, I will now go into some of the background on the Xbox boot process, just so you understand that. Firstly, the Intel CPU starts executing from the secret boot ROM, which is stored within the MCPX. This is a basic startup ROM. It's the first stage of bootloading. It does some basic setup, extremely basic, and then it runs a command interpreter called Xcodes. This is what the hacking community has called it. And Xcodes are stored in flash. They're on the flash chip. They're part of the BIOS. The Xcodes do various setups for PCI, for the video encoder, and for the memory. After Xcodes have finished executing, then the secret boot ROM hands over to the second stage bootloader, or 2BL. This can start its execution in flash, but often copies itself into RAM to execute much faster. One important point here is that for our exploits, for our homebrew software, we use an exploit called the Visor hack. And this Visor hack relies on there being executable instructions at address 0. Address 0 is in RAM. So basically, we need RAM working at address 0 to be able to use homebrew software. Finally, the second stage bootloader copies the kernel into RAM and then executes the kernel. The kernel is what does all the high-level operations of the Xbox, such as memory allocation. And for us to be able to use that additional 128 megabytes of memory, we do need the kernel to be able to see that memory and to allocate it properly. These are the essential steps to make 256 megabyte memory work on the Xbox. So firstly, in the Xcodes, we have to detect that extra memory. In the case that we do have the 256 megabit memory, then we can set the address mask accordingly, depending on how much memory is detected. We reconfigure the DRAM controller for the extra column bits. We reconfigure the auto pre-charge pin to be on A9 instead of A8. And if we detect the full 256 megabytes, then we enable the second rank. This enables the second set of 4 memory modules. And finally, there's the A8 and A9 bits in these two setup commands of the RAM. Going to the RAM's datasheet, then we can see the description of these commands. So MRS, mode register set, is a command that's used during initialization, and it uses the address bits as data bits. You can see A8 here is used as DR, which is the DLL reset bit. This can be quite important depending on how fast you want to clock the memory. In general, it is advised to always do a DLL reset. If we swap A8 and A9 in the hardware but don't swap them in the software, then you won't get a DLL reset. The eMRS does not have a similar issue because both of those bits are reserved for future use, so they don't do anything. Detection of 256 megabit memory is quite simple. We know that it can use the A8 bit as a column bit, and this is not possible on stock memory. So simply we need to be able to set that A8 column bit and see if the memory responds like a 256 megabit memory. By doing some reverse engineering, I found out this is how the address is broken down into the various parts of the system. So the A8 column address bit corresponds to bit 12 in the address. Since the stock memory will ignore that bit, then it will behave as if that bit is 0, meaning we can write to an address and check if it has been actually written to a different address. In that case, you know that it's 128 megabit memory. Here is that code implemented in Xcodes. So what I do is I write my magic word to address 1048, then I read back at 0048. This one here is bit 12. which corresponds to the A8 column bit. If the code was successfully written to the intended address, then we go to RAM setup done. Otherwise, we will reconfigure back to the default Xbox config. This is some early Xcode that does not detect the 128 megabyte configuration of 256 megabit memory. That's when you have 4 modules installed. If you don't detect this, then for Microsoft-based BIOSes, you can get issues such as a black screen, no video. So now that we've modified Xcode to satisfy that level, we need to make sure that the kernel is okay with extra memory. My first attempt at getting the kernel to be okay with the extra memory was to use EvoX. EvoX is a popular BIOS, and it has a patch to allow it to use 128 megabytes of memory. So what I did was I applied that patch and I loaded it up in IDA. IDA is a disassembler and decompiler tool used for reverse engineering. What I found is that some extra code has been injected here, and what it does is it modifies itself. The kernel, when it boots up, it modifies its own memory to modify the instructions, to modify constants that have been compiled in. So what's happened is that the source code is assuming that there is 64 megabytes, and those are hard-coded in. It is not variable. So the patch goes in and modifies all those constants to 128 megabytes. Given this, it should be a simple matter of remodifying all of those constants to make it work for 256 megabytes. However, I tried this several times, put loads of hours into this. I never got it to work properly. I believe I got a larger amount of memory to work, such as 190 megabytes, but I was not able to get the full 256. Where I got lucky, though, is that the executor BIOSes, the X2 and X3, they do not use constants. What they do is they read the RAM address mask and then use that. So it's completely dynamic. It's however much memory you have is however much memory will be available. This is really awesome because I don't even have to do any patching at all. All I need to do is change those Xcodes to get the boot working, and then it already knows there's extra memory. Another popular BIOS is SirBIOS. I tried modifying that. It does boot, but strangely, only if you are using composite video. Composite video kind of sucks. I think a lot of people with a heavily modded Xbox will not be using composite video, so I don't really see this as kind of feasible. I also modified the XBlast BIOS to have a test for that extra 128 megabytes of memory. So XBlast is often used for memory upgrades to check the additional memory, so I just repeated the same thing here. Except this memory is now double what was being tested previously, and the previous test was kind of slow in my opinion. So what I've done is I've changed the method of testing. Instead of testing each bit of every word individually, now I load in a pattern to the entire memory and I read it back. By doing this, the test is much faster, even faster than the original test, which tests less memory. One problem with this mod is that you're doing a full memory replacement of the whole system. So those first 4 chips that you put in are required for the Xbox to boot at all. You can't get to the XBlast memory test if you don't have the first 4 chips working. So this stands to be quite a large barrier to entry. How can you possibly know what's wrong with your memory without booting? To solve this, I crafted an XBlast variant that, in the flash code, it does a memory test. Then it blinks the front panel LED to tell you how it's doing. So it will tell you the status, which chip it's testing, and it will also tell you if a chip fails. In this case, that red, green, off blink is telling me that chip 2 has failed. This RAM test BIOS is based on flash code. So instead of copying code in flash to RAM and then executing it there, we keep the code in flash and we execute it from flash. This means that I don't need working memory for this BIOS to boot and be able to tell me which chip is failing. For the production test Xbox, I made a separate BIOS. Very similar though. It will just test a single chip, and it tests the entire memory of that single chip. If you've seen Macho Nacho's video, you'll already know this, but the extra 128 megabyte of memory isn't particularly useful for almost anything. It really is just a demonstration of capabilities. No game for the Xbox or even derivative Xbox systems was ever made with the idea that this much memory would be available. No homebrew has been made with the idea that this much memory is available. And so nothing actually uses that much memory. So you can do something silly like load in an 8K video, and the decoding of that video takes over 100 megabytes. But is that really useful? No. It's just a demonstration that that memory is working. So thank you for watching and all that. I really hope this was interesting, at least maybe even helpful to hackers, and I look forward to doing more of this in the future.